Welcome to The Explainer. Today, we're diving into something that sounds like it's straight out of science fiction. We're going to talk about how to teach an AI to understand the physics of a rocket engine that's smaller than a coin.
So yeah, how do you do that? And let me be clear, this is not just some futuristic thought experiment. It's a very real engineering problem. You know, designing systems on this tiny scale could completely change the game for future tech. Everything from positioning satellites in orbit to powering microscopic machines.
All right, so let's get into it. The tiny rocket problem. At the heart of all this are these little things called micro-nozzles. And while they're incredibly small, the physics happening inside them is a giant headache for engineers.
Okay, so these little engines work by shooting gas out at supersonic speeds. But here's the catch. When you shrink everything down to this microscale, the normal rules of fluid dynamics, well, they kind of start to break down. The physics gets unbelievably complex, which makes trying to design and test them with computer simulations a huge challenge.
And this slide really gets to the core of the problem. It's a real bottleneck. So on one side, you've got the gold standard simulation method, DSMC. It's perfectly accurate, it captures all the physics, it's the ground truth, but it's painfully slow. And on the other side, you have what engineers actually need, something super fast and cheap so they can run thousands of different designs. See the problem? The best tool we have is just too slow to be practical.
So let's talk about chasing an invisible wall. What is it exactly that makes simulating these tiny, high-speed flows so ridiculously hard?
Well, the answer comes down to one specific phenomenon. It's something that computers, and especially artificial intelligence, are just notoriously bad at understanding and predicting. It's called a shock wave. You can see it right there as that sharp red band. Now, think of it as an invisible wall where everything changes in an instant. Pressure, velocity, temperature, you name it. It's an abrupt, violent jump. And this one single feature is what breaks everything. Conventional models just can't handle it. And a standard AI? It just tends to smear or blur that critical detail into a fuzzy, totally useless mess.
So, how do you get around this? Well, to solve this problem, researchers came up with a completely new angle. They decided to change how we teach AI about physics in the first place. So, instead of just feeding an AI a bunch of raw data and then telling it, "No, you're wrong," over and over again, what if you could give it a hint? You know, a little clue about where the really hard part of the problem is. That's the core idea behind what they call a physics in the features approach.
The best way to think about it is like giving the AI a cheat sheet. Seriously. Step 1, you use a simple, fast model to just guess where that difficult shockwave is going to be. Then, and this is the clever part, you basically create a custom map for the AI that's centered on that shock. You're telling the AI, hey, pay attention, the tricky part is right here. By doing that, the AI can focus all its brainpower on getting that one critical region exactly right, which, it turns out, is a much easier problem to solve.
Okay, so that's the theory, a cheat sheet for AI. It sounds clever, but does this trick actually work in practice? To find out, the researchers put it through its paces, starting with a classic physics problem. And the answer is yes, it works beautifully. On a standard test that's well known for creating these shock-like features, the AI's prediction, that's the red dashed line, it almost perfectly matched the real solution in blue. We're talking less than 3% error, even when they threw conditions at it that it had never, ever seen before during training. So right away, they knew the concept was solid.
All right, now for the main event. What you're looking at here is the ground truth. This is that incredibly complex real-world flow inside the micro-nozzle we've been talking about. This is our target. This is what we need the AI to predict.
And here's the AI's prediction. I mean, just look at that. It's a near-perfect match. It's not just getting the general shape right, it's capturing the location, the intensity, and all those sharp, really difficult-to-predict details of the shockwave with incredible precision.
And if we slice right through the center of that flow and look at the hard data, the numbers confirm exactly what our eyes are telling us. The AI's prediction, that's the orange line, is perfectly tracking the ground truth data in blue. It even absolutely nails that incredibly steep jump right at the shock front. The accuracy here is just stunning.
Okay, so this level of accuracy is amazing, no doubt about it. But remember, for this to be truly useful for engineers, it also has to be fast. And this is where the new method goes from being impressive to being a total game changer.
And when I say fast, I don't mean just a little bit faster. This new shock-aware AI is orders of magnitude faster. We're talking about producing these super accurate simulations in a tiny fraction of the time it used to take. This is a monumental leap in speed.
So what's the big takeaway here? Why does all this matter? Well, this breakthrough basically lets engineers create an ultra-fast digital twin, a virtual copy of a real-world physical system. This completely unlocks rapid virtual prototyping. It means they can test thousands of different designs in the time it used to take to test just one. It's a whole new, much smarter way of blending AI with physics, and it could seriously accelerate innovation in tons of fields, from aerospace to material science.
And that really leaves us with a fascinating question to chew on. This research wasn't just about solving one tricky engineering problem, it was about finding a smarter way to work with AI. So, if we can pinpoint the hardest part of a problem and just give the AI a little cheat sheet to help it focus, what other problems, what other grand scientific challenges that seem impossible today are now suddenly within our reach?